welcome everyone. I am so excited today. We're starting a brand new section, vectors and scalars, and this is such a nice section because it helps explain a lot of science for us, which will hopefully put some things that you sort of knew instinctively into context. So let's get going. So, have you thought about, because this is a big thing now, how a fitness tracker describes your motion during a run? I have a fitness tracker, tells me I don't do enough, but when I go for a walk, because I don't run, how does it describe the motion for me? How does it describe where I went, where I ended, all of those sort of things? Those all are vectors and scalars. So actually, fitness trackers are very useful. Now, what are we looking at? So we're looking at motion. This whole section is part of motion in one dimension. Today, we're only going to look at vectors and scalars, but there's all of this other stuff to go with it, which we're going to do over the next few lessons. Keywords for today: vector, new term; scalar, new term; magnitude, size. Then we've got direction and resultant. Some of these are new terms. Some of them you may have heard before. Some of them are normal English terms. But we've got a couple there that are new, and it's part of the language of science. Okay, so we've got to make sure we get them down because we're going to use them lots in our science careers. So, and vector addition, I forgot about that one. That's definitely new. That's fun. We like that one. So we're going to look at vectors and scalars, and we can break up vectors and scalars into three specific places. We can look at their definitions, how we represent them, and what the resultant is. So looking at definitions, we're going to need to define what is a vector, and we're going to need to define what is a scalar. And these are physical quantities that have specific properties. So a vector has size and direction. A scalar only has size. Okay? Then we're going to need to look at how we represent them. And we're going to use an arrow, and that arrow has to have size and it has to have direction. You have actually come across this before in your junior years of science. You would have come across it when you've studied forces, okay? We're just now going to take that and put it into another context and give you the real science terms. You probably weren't given it as a vector. You were just told to do certain things, but it was a vector, okay? Then, of course, we have to get to what the resultant is. So we're going to need to define what we mean by a resultant, and the key is in the word that it's got result in the middle. Okay, so it's an addition, and we're going to talk about how we can get it. So either we're going to get it by construction. Construction means accurate diagram. So in this section, we need to make sure that we have a ruler where we can clearly see the millimeter marks on it, and it's nice and even. A sharp pencil. We don't like to draw our diagrams in pen. If you do, it's okay, it's not a problem. It's just the tip of our pens tend to be too thick. So our lines can be a little bit off and it can make a big difference. Okay, so we need to make sure we have the correct stationery. And then, of course, we can do it by calculation. Calculation, this is going to look a little different to what you're used to, because we now have to take direction into account. And that's where things can get a little hairy for us, because we're introducing a new way of looking at direction, and we're going to introduce a negative, but it's not the negative like you see on a number line. So when I have a negative number, it doesn't necessarily, well, it's not smaller than the positive number of the value, the same value. So -5 in vectors and scalars is not smaller than +5. The minus tells me direction for vectors, and I can already see you going, this is hard. It's not. It's nice. We like this. Okay. All right. So let's take a short break. You can think about what we've sort of discussed. And when we come back, we'll do it in lots and lots of detail. So get a glass of water, have a bit of a break, and I'll see you in a couple of minutes. Welcome back, everyone. Now we're going to look at vectors and scalars in detail. So we're going to look at definitions and examples and all sorts of things. It's such a nice section. Right, let's just get going. Once again, I want you to be thinking about how a fitness tracker describes motion, because it's actually a nice everyday application of what we're going to talk about. So just keep that in the back of your mind. Scalars. What is a scalar? Well, a scalar is a physical quantity. A physical quantity is something I can measure, like mass, time, temperature, all right? And a scalar specifically is a physical quantity that only has magnitude. So we can only measure how big or how small it is. It doesn't have a direction. When we define it, it's a physical quantity, so that's an important part here, is we have to make sure that we realize it's a, whoopsie, maybe I should have a pen that I can write with, there we go. Physical quantity, magnitude only, that means size. So we describe how big it is. And there's lots of scalars. These are all things where we don't worry about direction. We never describe it as going forwards or backwards or up or down. So something like mass. Okay? We never say that mass is going backwards, as much as sometimes we would like that. Okay? Which we measure in kilograms. Time, which we measure in seconds. We don't ever describe a direction as time. And in fact, we never give these two values in particular a negative value, okay? Because a negative value doesn't make sense. Energy is a vector. It has size, okay? Temperature is a scalar. Energy is a scalar, not a vector. I'm not doing vectors yet. Now here, temperature is a little different to the other ones, because temperature I can describe as negative. So I can go, it's minus 2 degrees today. That minus just tells me how cold it is. It's not a direction. It's still giving me the size of it. There are lots of scalars, okay? In this section in particular, we're going to look at speed, which we usually use. We'll tell you that the car was going at 120 kilometers per hour on the highway. We don't tell you which way it was going. We don't tell you where it was going. So that's just the speed. We're not telling you what direction it's going in. Another one is distance. And if we go back to our fitness trackers really give us distance. That's a scalar. If we have to actually go, so when I finish a walk and I look at my tracker, it'll tell me how many kilometers I walked, or meters, as the case may be some days. So it'll tell me distance, but I have to then go more into my app when I look at it to see exactly what direction I went in, because it doesn't tell me, it just gives me a distance. It says you went 2 kilometers and it took you 3 hours. I walk a little bit faster than that, but you get the idea. So then we get vectors. Now this is a new term for us, okay? And you've probably heard it. A vector is also a physical quantity, but it's a very special physical quantity because it's a quantity I have to describe not only how big it is, but I have to describe the direction it moves in, because the direction is very important. It helps us understand the motion. So vectors have to do with motion, have to do with things that will cause motion, okay? So a vector is a physical quantity again that has magnitude, size, and direction. And direction's the interesting one here. Because of the direction, we can have negative and positive vectors, and the negative means direction. The negative isn't about size anymore. And direction can be described in lots of ways. Left, right, up, down, north, south. We're going to talk about them. We're going to explain them all, okay? So what are our examples of vectors? Things like velocity. Now, velocity is very similar to speed, and it's possible for an object to have the same magnitude of speed as velocity, but velocity, I need to know which direction it went in. So if I'm going to describe the velocity of a car on the highway, I would go, the car's going at 100 kilometers per hour north. Okay? I have to tell you where it's going. I have to tell you where it's heading. What direction is it going in? If the next one, which you have sort of dealt with before, is force. We just didn't call it a vector. Okay? Which, of course, we're measuring newtons. You know forces are pushes and pulls. So if I tell you I'm exerting a force on an object, that doesn't really tell me very much. It doesn't give me any information. But if I tell you that I'm pushing a box forward with a certain value force, that makes sense. I can now use that information. I can now describe the motion. So here our vectors are quite important, okay? Another one, and we're going to see it often in this section, is acceleration. And here, acceleration is about how much faster an object is moving every second. We're going to define it all again in later episodes. We'll get there. But acceleration is absolutely a vector, because we can have acceleration that causes an object to go faster, and we can have acceleration that causes an object to go slower. They have different directions. And we've got to sort of get this direction thing in our heads. It's the direction that gets a little hairy for us, okay? But we can do this. So, how do we represent a vector? We don't generally draw diagrams to represent a scalar because it doesn't have a direction, okay? But we represent them with an arrow. This arrow has a couple of things we need to take note of. Number one, the size of the arrow equals the size of the vector, or it represents it. I can draw these to scale, so I can tell you that I want a force of 10 newtons, and I want the length of the arrow to be that every centimeter equals 1 newton. You've done that in other subjects where you've had to work with scales. Generally, if we don't do it by construction, it's just a relative thing. So it's showing me the size. So if I have a big vector, I draw a very long line. If I have a small vector, I draw a small line. It doesn't matter what vector I'm representing. It's all represented the same way. The arrow part shows me the direction. That means this vector, as it's drawn, is showing me a vector going to the right. Okay? If the vector needed to go to the left, I'd turn it around. If it's a vector showing me something going up, I'd point the arrow upwards. So where the arrow points is important. It shows me the direction. We then have some parts on the arrow that we give names to so that everyone understands what we're talking about. This part of the arrow, the beginning, is called the tail. Okay? This part where the arrow is called the head. Okay? So if I start talking about drawing diagrams, head to tail, I mean I want the arrow to go to the back of another vector. Okay, so head to tail is quite important. When we also draw a vector, we need to give it a label. By a label, either we need to put the size of the vector on it, 10 newtons, 100 kilometers, whatever it is that we're measuring, or we need to give it a name, so we call it F, or we give it a V for velocity. But I've got to tell you what the arrow is, otherwise it's just an arrow. What does it mean? You need to explain that to me, okay? Now we need to talk about direction. Direction can be described in a couple of ways. The easiest for us is when they go to the right. That's nice, it's horizontal. Or when they say it's going to the left. Those are easy, those are nice. Left, right, we can do that. Or of course we can go up and we can go down. Those are easy directions. We're okay with those because it makes sense to us, left, right, up, down. And we're actually nice in that when we start this, we keep it all in one plane. So I'm not going to include all the time, every now and then we do, something that's going left and right with something that's going up and down. Okay, it depends on the question we're asking. But those are nice. But what happens when we don't use those? Because in reality, we're going to use the cardinal points. So you know the cardinal points. You've done this in other subjects where you've got north, south, east, and west. Please make sure you can know which they are. If we look at the cardinal points, so this is north, that's south, oh, that's not south, that's east. This is why you have to learn it. Okay, so that's east, that's south, and that's west. If I describe it as north, south, east, west, usually we're okay with that. Or if I had to tell you that something was going northeast, we're okay. We could draw northeast. Okay, you've done that. The issue comes in when I use a thing called bearing. Because actually, we want our directions to be as accurate as possible. And bearing is actually more useful. Bearing is not like the Cartesian plane in maths, okay? So remember, with bearing, north is 0 degrees. East is 90 degrees. South is 180. And west is 270. We also measure our angles from north, from 0, okay? And maths, you normally go to the left when you measure. With this, we measure to the right. So we start, I'm just going to get rid of my northeast line quickly. So here, we start at north and we measure around like this. And that feels a little funny, but it's really important. So if I said to you that we had an object that was moving at a bearing of 80 degrees, okay? So I'm going to do a bearing of 80. What that means for me is I take that away, and my bearing, I measure 80, and it does that. That's 80 degrees, okay? When we're looking at the Cartesian plane, I just want you to see the difference. This is 0, that's 90, that's 180, and that's 270. And now we measure the angles that way around. We don't want to use the Cartesian plane. We're going to use cardinal points. Then we get the resultant. Now, the resultant is a single vector that has the same effect as 2 or more vectors together. In other words, I have 2 vectors, or 3 or 4, and I say if I took all of those away and replace it with a single one, what must the size and direction of that vector be so that I have the same effect, I have the same thing happening? So we take lots of things, make it into one. Result, okay? There's 2 ways we can do this. By a scale diagram, in other words, by construction, and we can do it by calculation. I prefer calculation, but construction helps us understand, okay? So for example, We have two forces, 50 newtons and one of 30, acting on a point in opposite directions. So if we want to, we can say there's the 50 newtons going in that direction, and we have 30 going in that direction. Logically and instinctively, I think most of you can tell me what the result of these two, it's like a tug of war. You'll be able to tell me that it's 20 newtons going, in this case, because I drew it to the right, to the 50 newton. If I do it by a construction and we would measure this, we would go 50 newtons here, 30 newtons there, and my resultant goes from here to there, and that's 20 newtons. Okay, my resultant starts at the beginning of the first one and ends at the end of the last one. No matter how many I've got, I just draw lots of arrows from left to right and up and down, okay? I could do this by calculation. Now here, this is where life gets interesting, because I'm going to do a resultant, and this is vector addition. So I would add the two together, but they're in opposite directions, and I'm going to tell you that this one is in a positive direction. This one is in a negative direction. I'm not saying to you it's minus 30. I'm saying to you that the negative gives me the direction it's going in. Doesn't mean it's small, okay? So if this is my first force, then this is 50 newtons. I'm going to add this one, but it's minus 30, and that gives me 20. But now I don't have a direction that I can see. Here I can see the direction for the construction. So I said this was my positive direction, and we're just going to go with what I wrote. We'll be more specific with directions. So this is positive, so that means that it's going to the right. So we just need to pay attention to whether we want a diagram or whether we want a calculation. Either way, we get the same answer. Guys, we've just done a lot of stuff now, so I think it's time for us to take a little bit of a water break, refresh our brains. So go get some water, quick run around the lounge for 2 seconds, and I'll see you in a couple of minutes. Welcome back, everyone. Now let's see if we can apply the theory, okay? Sometimes when we look at questions and we look at things that we need to think about what we just learned, it makes it easier. First question, classify, so we're going to break them up, each of the following as either a vector or a scalar. So what we mean by this is, how do I know? What we're relying on is for you to think about the quantity and go, would I describe that with a direction? If the answer is no, then it's a scalar. If the answer is yes, then it's a vector. Okay? So, here we go. Here's our list again. I'm going to make one side, I'm going to do it as a table. So here's my scalars. And here's my vectors. Let's see. First one is time. As much as I would love to describe time going backward, I can't. So time is definitely a scalar. Ooh, weight. Remember, weight isn't mass. Even though we may say to someone, what's your weight? We're actually asking what's their mass. Weight, you've learned before, is a force. Forces need a direction. So weight is a vector. Mass. Mass doesn't have direction. Of course it doesn't. We just say something is 2 kilograms or 100 grams. We don't describe it as being anywhere. So mass is definitely a scalar. So we've done those. Charge. Charge, we get positive charge and we get negative charge, but that's just the size of the charge. That's because we get positive and negative charges. That's not a direction thing. So charge is a scalar. Okay? Charge is a scalar. Force, well, if I've just said to you weight is a vector and weight is a force, then force must be a vector. Must be. Okay? Ooh, speed. Be careful. We will say they have a speed of 20 meters per second. Or a 100-meter runner runs at a speed of 10 meters per second. We don't describe speed with a direction. So speed is a scalar. Acceleration, absolutely a vector. Acceleration, I need to know whether the acceleration is causing a speeding up of a motion or a slowing down of a motion. So acceleration's a vector. Oops. Distance. Distance, like when my fitness tracker tells me that I did 4 kilometers, it's not telling me how I went, where I went, unless I look at the map. It's just saying you did 4 kilometers, okay? Distance is a scalar. I'm going to run out of space here soon. All right. Temperature. Yes, I get positive temperatures and minus temperatures, but that's not because the temperature went backwards. It's just colder. It's just the way we measure it. So a negative temperature is still a magnitude. That means temperature is a scalar. Volume. The volume of a glass, the volume of a cold drink. Volume, milliliters, centimeters cubed, whatever we measure it in. Volume's also a scalar. We don't go, the volume was 3 liters backwards. What does that mean? Doesn't have a direction. So volume is a scalar. Now, in this particular list, I had a lot of scalars. And only because we're still introducing new vector concepts to you. There are lots of vectors. However, there's probably far more scalars. Just because of the way physical concepts are, physical quantities. We're not going to get too hung up on that. Now, I want a vector diagram to represent the following vectors. 20 newtons east, 30 meters per second bearing 180, 125 kilometers southwest, 25 newtons right, 0,03 newtons up. Now, I'm just saying I want a vector diagram. All I want to get in these questions is, can you draw the vector at the correct direction? These will be sketches. I can't draw them to scale, but it's worth practicing them to scale, okay? With a protractor, with a ruler, drawing them nice and neat, okay? I struggle because I don't have a ruler on this, and I can't draw straight lines on my own. I need a ruler. So I want you, while we're doing it, to have a ruler and a pen and piece of paper and draw it nice and neatly, okay? Mine are definitely only sketches. So if we look at the first one, I want 20 newtons east. As a convention, we will do north going up. I need to know where north is on your page because we conventionally make it going up, but it doesn't have to be going up, okay? As I'm here in the studio, I actually don't know if I'm facing north. So I can't tell you that east is to my right, which is what this says, okay? Because I don't know where north is. I'm a little directionally challenged sometimes, okay? That's why we need GPSs on phones and things, okay? But I can't just assume because this is the direction I'm facing that that direction is east. It's very likely not east, okay? And that's the important thing. So I need to indicate on my diagram where is east. Well, where is north? North is up. Then they said we've got 20 newtons. If I'm going to do this to scale, okay, we would go, there we go. I'm going to draw a straight line, 20 newtons like that, and say I used a scale, 1 centimeter is 5 newtons. It'll be 4 meters long. 4 meters, that's ridiculous. 4 centimeters. Okay, you don't have a page that's 4 meters long. So we have to choose a scale that we can fit on our page. Okay, next one. 30 meters per second, bearing 180. So remember, again, I need to know where north is. We know that the bearing gets measured from north, and it's going to be 180, which is there. Then it goes straight down 30 meters per second. It's a different type of vector. It's a velocity. So I label it as 30 meters per second, but it's bearing 180. That's not so bad. 125 kilometers southwest. So again, here's north. Now this is southwest. Here's south, there's west. So it's going to be in the middle of those two. This time, my vector is now going to go over there, and it's halfway, and that's 125 kilometers. For one like this, where it's a very big number, going, even if we went, for example, 5 centimeters is 5 kilometers, we would never be able to fit this on our page, because we would have to go 125 divided by 5, and the line's just going to be too long. So probably what we would do is we'd rather go, no, I'm lying, I would go 1 centimeter is 10 kilometers, because then the line would still be 12.5 centimeters. Okay, it's still quite long. But when we draw vector diagrams, the bigger we can draw them, the more accurate they become, which is what we want. Then we've got 20 newtons to the right. Now here, I'm not describing north and south. I'm just simply going to the right. So draw it to the right. Don't draw it in any other direction and tell your teacher I turned my page around. Okay? As we read the page, that's how we're going to get right or left. So I would simply draw a line, 25 newtons. And this one, to make it a nice size line, a good scale would be 1 centimeter is 5 newtons, because then my line would be 5 centimeters long. That's long, but it's a good scale. It's a very good scale. Oh, now we've got a little one. Okay. So we've got 0.03 newtons. It's going up. Here, we would do the scale a little differently, because now it's not a big force. It's quite a small force. And we probably wouldn't ask you to draw one like this to scale, because it's small. Because here you would probably need to go something like 1 centimeter is 0.01 newtons, because then my line would be 3 newtons, okay? But what I would wanting you to get is that it doesn't matter what the vector is, we still draw it with a line that's a specific length at a specific direction. Okay, that's very, very important. We got through that. Time for a short break, and then I will see you in a couple of minutes. Welcome back. Now, let's do some more complicated questions. Let's see if we can find the resultant of a whole bunch of vectors. Okay, so we're going to dive right in, because we like this section. All right. First question, 2 boys pull a crate to the right. giving you direction. One boy pulls with a force of 20, and his friend pulls with a force of 50. Then I say determine the resultant. Now we need to get used to the language, okay? I've said determine the resultant. I haven't specified for you how I want you to determine the resultant. Remember, we can do it by a calculation, or we can do it by construction. So we're going to do it both ways, because I want you to see that it doesn't matter. If the question had said calculate, I'm telling you how I want it. If the question had said draw by construction, draw a scale diagram, I'm also telling you how I want it. But this said just determine. So let's look at it with a diagram. They both pull to the right. So that's going to be my positive direction. I'm going to call this force F1, and I'm going to call this one F2. The only reason being the 20 was given first, the 50 was given second. If I did it by construction, I would draw an accurate line of 20 newtons, which is going in that direction. Then I draw another accurate line of 50 newtons going in that direction, and I draw it one after the other, head to tail. My resultant is always from the beginning of the first one to the end of the last one. You have to get that stuck in your brain because you're going to use it lots over the next few years, okay? From the beginning of the first one to the end of the last one. So here's the beginning of my first one. Oopsie, it goes all the way to there, and we would then measure it, and it gives me 70. But I need to write down what the resultant is. So I say my resultant force is 70 newtons right. That's by construction. If I do it by calculation, I now need to go my resultant force is my first force plus my second force. My first force was 20. My second force was 50. So that's 70 newtons. And it's positive, not that I could get a negative. It all went to the right. I still need to say to the right. I'm finding a vector. A vector must have size and direction. I need to know where it's going. Good. A girl pushes a heavy box with the force of 50 newtons to the right. Another girl is also pushing on the box, but she's pushing with a force of 70 newtons to the left. And again, determine the resultant. Now, instinctively, you can all tell me that if one girl pushes to the right and the other one pushes with a bigger force to the left, the box is going to go to the left. You can do it instinctively. It's just part of your makeup. It's not something you actually think about twice. But we need to put it in scientific terms, which is what we're doing. They said again, determine. So I don't mind how we do it. So we're going to do it both ways. We're going to do it by construction, and we're going to do it by calculation. So, starting with this one, we have a 50 Newton force to the right. There's my first one. Then I have a 70 Newton to the left. Now I start at the head of the first one, and I go 70 newtons to the left. Remember what I said to you? The resultant is from the start of the first one to the end of the last one. So my resultant is there. We would then take out our ruler and we would measure it because this is accurate. And what we should get is that that's 20 newtons. So I would go, my resultant is 20 newtons left. And instinctively, we knew it would be left. We just now have the size. Let's do it by calculation. What I like to do is I like to go what is a logical choice for direction, but it actually doesn't matter. If you want to always be doing the same thing, choose the original direction. Whatever direction you get given first, make that your positive direction, because then you've got a system. So I'm going to make to the right positive, which means to the left is negative. This is my first force. This is my second force. So when I do the addition, I go my resultant is my first plus my second. My first is 50. My second now becomes minus 70. That minus is important because it's direction. It's telling me that it's in the opposite direction to the 50. That, I need to know that. If I do this and we go 50 minus 70, we're going to end up with minus 20. We now have to be careful. That minus 20 is telling me that it's going in the left direction. But when I give my final answer, I never use a negative value. If I have to do a calculation with this, then I use it. But this negative value gives me direction. So I'm going to describe it. I'm going to go, that means that my resultant is 20 newtons left. I always leave my answer as a positive answer with the direction in words. I know the negative means a direction. I know it implies a direction. But I want it in words. Very, very, very important. I could have chosen to the right is negative. The difference will be that I will end up with a positive answer at the end, which then means it's going left. It doesn't make a difference, okay? There we go. We have a runner. He's training on a flat, straight road. She runs 10 meters north, 7 meters south, and then 125 meters north. We want the resultant. So what has she done? She went 100 meters north. So I'm making this direction my north. So that's 100 meters. She then went 75 meters south. And then she went 125, I should have drawn this differently, 125 meters north. Now I need to know the resultant, and this was a very bad diagram. My resultant goes from here to there. No, I lied to you. My resultant goes from the beginning of the first one to the end of the last one, and this is why you draw it better than I did, because you don't go into your writing. This, when it's lots like this, it's much easier to do this by calculation. So what I'm going to do is I'm going to say north is positive. Okay. I can't use F because F means force. I've got a distance here. Okay. So I'm going to go, her resultant is going to be her first distance, which was 100, minus her second distance, which was 75, plus the 125, okay? So let's just get this, do it on our calculators. So we've got 100 minus 75 plus 125 and we get 150, and we get a positive 150, so she ended up 150 meters north of where she started. And I'm not sure that was expected. I'm sure some of you went, that was a bit further. I'm not talking about how far she ran, it's just where she ended up compared to where she started. Okay, that's her resultant. So she could have got to the same place by just running 150 meters north, instead of going 125, 125. But she was in training, so that's what we do. Okay? So, there we go. And lots that we did. So remember, direction, direction, direction. You can find resultants by construction or by calculation, but only for vectors. For scalars, you simply just add them all together. Wow, lots to think about, lots of new concepts. But it's okay, the more you practice, the better you get. So we're going to stop there for today, and I will see you next time.